So today we are still on the 2006 MIT Integration B regular season, and we're moving from round 2 and 3 to round 4 today. So I hope you stay put and you enjoy our versions of the solutions to some of the problems that were presented. Uh, and some of our solutions obviously overlap with what was provided, but we hope you do enjoy our foray into this. Problem number one of round 4 was the definite integral from x equals to 0 to x tending to infinity of 2x squared plus 1 times e to the power negative x squared. And it's certainly a very interesting problem. And this here tests one on the knowledge of a Gaussian integral. So let's go quickly and see how to solve this. So as we said, our problem is the integral from x equals to 0 to x equals to 8 of 2x squared plus 1 times e to the power negative x squared. So we can decide to split this into two separate integrals, and I've decided to color code them. So we bunch the 2x squared e to the power negative x squared into one integrand, and then the other one the green integral into just 1 times e to the power negative x squared. From here, clearly we can see that this part here can be looked at using the Gaussian integral. And the Gaussian integral is if you have e to the power negative x squared integrated from x and negative infinity to x tending to positive infinity, you get the square root of pi. And since this function is symmetrical, it's literally symmetrical about x equals to 0, then it means that from 0 to pi, this is half of square root of pi, right? So we can just quickly go in and plug the square root of pi over 2 in place of the green integral. So square root of pi over 2 replaces the green integral. Now we're left with our first item, and we can see that this can also be expressed as x times the derivative of negative e to the power negative x squared, and it's obviously inviting for us to see that this can be solved using the partial integral technique, where if you have a product of a function v and the derivative of function u, the answer is uv minus the derivative of u times the derivative of v. So we can take, in this instance, u to be negative e to the power negative x squared, such that uv in that instance is negative x times e to the power negative x squared, and then the next integral becomes minus the integral of negative e to the power negative x squared times the derivative of x, which v was x. So this here just tends to 1, right? And the two signs here interact so that we have a positive. So we have plus the integral of e to the power negative x squared. And so we see that we have a second half Gaussian integral here, and we can replace this with as well square root of pi over 2. The next thing is we have to deal with this part here where we have to look at the limit as x tending to infinity on the upper side and as x tends to 0. So that happens, as you see, as x tends to infinity, this part here tends to 0. Or you can look at it from a way where this is the denominator and you do a derivative and you're left with 1 over negative x, and this obviously tends to 0. So this part here tends to 0, definitely. You could use L'Hopital to work on that. And then this part also tends to 0 because we have 0 here, and this tends to 1, so we have this also tends to 0, right? And we say this here is square root of pi over 2, right? So you have square root of pi over 2 plus square root of pi over 2, and that becomes square root of pi. So in other words, when solving the integration of 2x squared plus 1 times e to the power negative x squared from x equals 0 to x tending to infinity, you get square root of pi. And that was the answer that was required of us. 2 of that round 4 was the integral from x equals 0 to x equals to pi of the product of cosine of 7x, cosine 17x, cosine 37x. This is certainly a very interesting problem, and let's see how we may be able to solve it. So this problem, without really even doing anything, the answer is 0. And for us here, the mantra is sometimes it pays to be lazy. Instead of jumping in and writing a lot of stuff, it just pays to investigate the integrand you have at hand and then know the solution. So this, how I would be able to guess that this is 0 is, first, there's one thing you have to look at. When you look at the integral of cosine of nx, where n is an integer, that's the same as from 0 to pi is the same as 1 over n sine nx from 0 to pi, and then we substitute the limits, you get 0. So why is this important? It is because I can decompose this product that we have here. This product can be decomposed, the product here can be decomposed into independent cosine functions with different values of n here. So, and this is very important to see that if you have cosine A plus B, that's the same as cosine A, cosine B minus sine A, sine B, and cosine A minus B, the same as cosine A, cosine B plus sine A, sine B. And then if you add this, so you add this and this, you get this and that would cancel, and so you have 2 cosine A, cosine B. And so making cosine A, cosine B the subject, you have cosine A, cosine B is equals to a half cosine AB plus cosine A minus B. So from this product of cosine functions, I can create 2 independent cosine functions, right? And A plus B, if A and B are independent integers, then you can see A plus B and A minus B also yield integers. So you have functions that have integer n's in their arguments. So, so with this, for example, let's just do a quick experimental view of it, then we'll go into the deep solution to it. So you have cosine 7x times cosine 17x. These two here can be solved into using this analogy here. We have k prime, which could be some fraction, which is cosine x plus cosine bx times cosine 17x, obviously. And then when you multiply this across by this and by this, you have 2 products again, still k prime as a constant, so you have cosine x and cosine 37x plus cosine bx times cosine 37x. And this again yield a sum of 2 functions. So finally you have cosine k double prime, cosine cx plus cosine dx coming from this product, and then triple k triple prime cosine EX plus cosine FX coming from this product. And you see, since we've seen that the integral from 0 to pi of any integer multiplied by x, cosine of any integer multiplied by x, this is equals to 0. So this would be 0, this would be 0, this would be 0, this would be 0, yielding 0. So that is the quick process that would work out in my mind to find that this is actually 0. So let's jump into the actual solution to this problem, right? So if you are the person who is not lazy, then you'd like to do the actual mathematics, the first thing is, okay, you'd look at this, and this is the same as half cosine 17x plus cosine 7x, close brackets, plus cosine 17x minus 7x. And this becomes obviously half times the integral from x equals 0 to x equals to pi of cosine 24x plus cosine 10x. And then you multiply cosine 37x through, so you have half times cosine 24x times cosine 37x plus cosine 10x times cosine 37x. Now you can now break down these two different products separately. So you have now half the integral from 0 to pi of half times cosine 24x plus 37x plus cosine 37x minus 24x, close brackets, plus a half cosine 37x plus 10x plus cosine 37x minus 10x. This becomes half of the integral from 0 to pi of half of cosine 61x plus cosine 13x plus half, open bracket, cosine from this, so you have cosine 47x plus cosine 27x. And then we can pull all the half out, so you have a quarter, the integral from 0 to pi of cosine 13x, we are arranging it in the increasing order, 13x, 27x, cosine 47x, cosine 61x. So when you integrate these functions independently, we have a quarter of 1 over 13 sine 13x plus 1 over 27 sine 27x plus 1 over 47 sine 47x plus 1 over 61 sine 61x. And the limits here applied appropriately, 0 and pi. So from those limits, we see that we have 1 over 13 sine 13 pi minus sine 0 plus 1 over 27 sine 27 pi minus sine 0 plus 1 over 47 sine 47 pi minus sine 0 plus 1 over 61 times sine 61 pi minus 0. Sine of any integer value times pi is 0, so this tends to 0, this tends to 0, and also the sine of 0 is 0, so this is 0, 0, 0, 0, and 0. And so everything collapses to 0. So it's a quarter times 0 throughout, and that is how we get our 0. So on to problem number 3 of the same round 4. We have an indefinite integral of sine 101x times sine x to the power 99. Again, a very interesting problem. So let's see how we may be able to solve this. Obviously, the contestants were not able to solve this in the allotted time, but it's a very easy problem to solve. So personally, what I would do with this problem is that I would focus on this first part here. And that is the same as sine of 100 plus x. So 100x plus x times sine to the power 99x. So using expansion of sine a plus b cosine a cosine b plus sine b cosine a, we have sine 100x cosine x plus sine x times cosine 100x times sine to the power 99x. So multiplying it across, we have sine 100x times cosine x times sine to the power 99x plus this sine here and this interact, so we have cosine 100x times sine, this is 100 x, because 99 sine to the power 99 times 99x times sine x is that. And this now we can see is the same as sine 100x times the derivative of 1 over 100 of sine 100x plus sine, this is sine 100 times the derivative of 1 over 100 times sine x. And knowing that if you have the derivative of a product of two functions, so let's say you differentiate v and u, you get v du dx plus u dv dx. Knowing this, we can already see that this part is what we have under the integral sign. So we can now say that we can pull the constant out, 1 over 100, and we have, first of all, this is 100, and we have that, and this now becomes 1 over 100, the integral of the derivative of sine of 100 x times sine of to the power 100x. And since this integral sign is an antiderivative, whatever the derivative or the differentiation sign creates is destroyed by the integral sign. So this function here remains immutable, obviously with an integration constant. So this becomes 100 times sine 100x times sine to the power 100x, and plus integration constant. And that is the answer that was required of us, as simple as that. Problem for round 4, the indefinite integral of cosine of 4x plus 1 over cotangent of x minus tangent of x. This is certainly it looks ugly, but this is a problem that one of the contestants was able to solve very fast and won this round. So let's quickly go and see how to solve. So I personally would express cotangent x and tangent x in form of the elementary sine x and cosine x functions. And that's what quickly, we've been able to do here, right? And so the common denominator here would be cosine x sine x. And that's what we're going to do. So we have cosine 4x plus 1 over cosine squared x. So cosine x sine x divided by sine x is cosine x times cosine x. We get cosine squared x minus sine squared x. Now, since we know that sine 2x is equals to 2 sine x cosine x, we see that a half of sine 2x is equals to sine x cosine x. And so we can now express cosine x sine x in form of sine 2x. And that's what we went ahead to do, right? And we can bring this guy on top so that we have half the integral of cosine 4x plus 1 over cosine squared x minus sine x times sine 2x at the top. And this cosine x minus cosine squared x minus sine squared x is the same as, since cosine 2x is equals to cosine squared x minus sine x squared x, we can express this in form of cosine 2x. And what that allows us to see is that the sine 2x at the top and the cosine 2x at the bottom will interact to form, these two would interact to form tangent of 2x. Okay, which is obviously interesting. We can also go ahead and try to eliminate this 1 here by expressing cosine 4x in form of twice cosine 2x minus 1, right? So we have tangent x and we want to eliminate that 1 there. So 2 cosine squared x, 2x minus 1 plus 1, this and that would cancel. So we do have half times cosine, twice the cosine squared 2x times the tangent of 2x. This and that would cancel. So tangent 2x is equals to sine 2x over cosine 2x. And that's where you see one of the squared, the 2 cosine 2x in the numerator goes out. So we cancel that squared with that. And so you realize that you have the integral of the product for cosine 2x and sine 2x. And going back to the formalism where we have sine 4x is the same as twice sine 2x cosine 2x, such that a half of sine 4x is equals to sine 2x cosine 2x. So that now comes in here, and this product becomes a half of sine 4x. So our integral becomes that. So we have a half, and when you integrate sine 4x, we have negative 1 over 4 cosine 4x. So the answer becomes negative 1 over 8 cosine 4x plus the integration constant. And that was the answer that was required. So that caps up round 4 of the 2006 MIT Integration B regular season. I hope you did enjoy our versions of the solutions. So if you have any question, as mentioned earlier, please don't hesitate to leave a comment in the comment section. But also, if you haven't subscribed to our channel, we do really encourage you to subscribe to our channel.